Okay, we're going to start a new unit on principal component analysis. How many people have heard of PCA? I'm curious. Nobody's heard of PCA? Okay. It's a buzzword that comes up a lot. I thought maybe someone would have heard of it. So, so basically, PCA is used for dimensionality reduction. So what is that? The idea is that a lot of data sets have high dimension D. D is the number of features. And there's many reasons why we might want to reduce the dimension. We might want to have fewer features to use in our classification or regression tasks. We may want to store or transmit those features with less memory or bandwidth. And if we can reduce the feature dimension down to 2 or 3, then we can actually visualize the structure in the data. And so the most famous approach to dimensionality reduction, the most basic, is known as PCA. And PCA is basically the RSS optimal linear dimensionality reduction. So those are the two main ideas. It's linear and it's RSS optimal, so it plays a similar role to when we studied linear regression. That was also RSS optimal linear, but there the goal was prediction or regression, and now it's dimensionality reduction. And towards the end of the unit, we will briefly talk about a couple modern techniques that are used for visualizing structure and data. They're complicated to describe how they work, so we won't get into that, but I just want you to be aware of them because they're useful tools for visualizing data. Okay, so in this unit, our data set is going to be very simple. It's just going to be these n feature vectors xi. So in other words, there's no targets or labels in the data anymore. It's just these feature vectors. And each of these feature vectors is the same as we're used to. It's just d real numbers. And so if we want to stack those vectors as columns of a matrix and then transpose that matrix, we get the same X matrix that we saw back in Unit 2. And we are going to assume, to make the derivations easier, that the data is centered, meaning we have computed the sample mean and subtracted it, so that basically when we look at the sample mean of our new features, it's 0. Okay. This is not essential for the ideas, but it just keeps our derivation a little bit easier. So again, there's no targets or labels in our data set now. Now, maybe we do have some, we'll just ignore them for this purpose. And so this is an example of what's called unsupervised learning, because without those targets, those are sort of usually the supervision for how we learn our system. They're absent, so we're doing a different kind of learning. Supervised learning would include like classification and regression. Unsupervised learning would be something like this, dimensionality reduction, or clustering, which we'll talk about in the next unit. So basically the question now is, can we somehow compress our features without losing much information? So that's our goal. So there's, again, two main ideas behind PCA. Number one, it's linear, and number two, it minimizes RSS. So what do we mean by this linear approximation? It means that each of our feature vectors xi is going to be approximated by some matrix B, tall matrix B, times some coefficients zi that depend on the index of X, the index in our data set. Whereas this B matrix, you can see, is the same throughout the whole data set. So this B matrix, we can think of it as a dictionary. Its columns are like some atoms that we can linearly combine using the coefficients in zi to get our approximation of xi. So that's basically how we set this up. We get to choose how many columns are in the dictionary B, or how many coefficients are in Zi, and that's called the rank of the approximation. And so intuitively, if you use many columns in B, then you get a better approximation than if you use few. But you also get less compression. So this is just a trade-off that we have to make. When we do this, like, do we want to have a lot of compression or a little? And this is a lossy compression. It's not like lossless compression. This is lossy. When you use a small r, you don't have a perfect equality. So the key thing here is that we call it linear because basically, it's xi is a linear combination of some columns, linear, and the zi is linear in the b's, I guess, but kind of linear in both. Okay, so is this part clear how we're doing our approximation? Any questions on that? Okay, then the second main idea is that we're going to design the matrix B and all those coefficient vectors Zi to minimize RSS. So here is RSS for the ith vector, and then here is summing over our data set. And so in spirit, this has a familiar form to us, except it's a little different from what we've seen previously. When we saw this back in Unit 2, we had some labels Y here, we had a matrix A, and we had some coefficients beta. But now, we don't have any labels, so we have our features. We're trying to match those with this approximation. And this is the problem that's solved by PCA. So we're choosing RSS because it's tractable and simple. It's not necessarily what you want to use in all cases, especially if you are doing this compression with the goal of taking the approximated features and doing something later with them, like classification. You might actually lose the information most useful to classification might be lost through this process. And I'll show you an example of that later. There are other ways to do dimensional reduction, like, so this is just probably the most famous one and the one that people use and talk about most. It's a very old idea, probably like 100 years old or more, but it's so fundamental that I thought it would be useful to talk about it in a class like this. So that's kind of setting up the problem, and then what we're going to do next is we're going to solve it with the math, and then we'll demonstrate it with some data. But are the main ideas clear, at least? Any questions? Okay. All right, so I'll give you a preview of the solution and some of the intuition behind it before we actually dive into the derivation. So basically, it turns out that the way that you select the dictionary, the optimum dictionary, which we'll call B hat, is you can construct it by taking what are called the principal eigenvectors of the sample covariance matrix and stacking them in columns of a matrix. And so, okay, the sample covariance matrix, this is something we talked about way back, I guess, when we were talking about statistics, talked about covariance. And we're not subtracting the mean here because we already subtracted the mean. That was one of the assumptions, that we have basically zero mean data. The sample mean has been subtracted out. So therefore, this is the covariance matrix. So you take this matrix and you do an eigenvalue decomposition. One way of writing that decomposition is this. We'll get into the details later. But these things, the VJs are the eigenvectors, and the lambda J's are the eigenvalues. And generally speaking, if this is a D by D matrix, because our features are D-dimensional, you need a total of D of these components to get the exact fit to this. But what is done in PCA is, instead of using all D of them, you only use the first R, meaning the VJs, that correspond to the largest R eigenvalues. Those are called the principal eigenvectors, the most important ones. And basically, you construct your B matrix with those V's, and then you can compute the coefficients by taking that same V matrix and doing V transpose times the full feature vector, and that will reduce the dimension down to R. Okay, so what are we actually doing in all this? I think these pictures will clarify it. So in these pictures, on the left picture, we have a data set with 3 features, and you can see we're plotting those 3 features on these axes. And we're saying we want to compress those features down to 2 dimensions. That means we're looking for a plane, a 2-dimensional plane in this 3-dimensional space that minimizes the RSS. The RSS, so the error from each one of these are the original samples. You can ignore, the red and green is really just showing you on which side of the plane they lie on. There's no like classes or anything. But this is the original data. This would be the PCA approximation, the stuff that's exactly in the plane. And so the error in the approximation would be those lengths, and we want to minimize the sum squared error. So we want to tilt this plane around so that this sum squared error is minimized. And because this is a subspace, it must pass through the origin. So I don't know if that's not necessarily clear in this picture, but that's basically how it's set up. Okay, so basically we're looking for a 2-dimensional approximation of the 3-dimensional data. We're looking for the best one in the sense of minimizing RSS. Now you might say, well, what happens if I want a 1-dimensional approximation of the same data set? Well, in that case, instead of a plane, you actually have just a line. And so now you want to find, and here's the approximation, are the points along the line, and this is your original data set. So now you want to minimize the sum squared of those errors. Okay, so basically that's the idea. You're looking for the best approximation to your data that lives in some hyperplane of dimension R. You get to choose R. You know, the smaller R is, the bigger the error is. So that's a trade-off that you have to make. We'll talk about that trade-off later. So that's basically what PCA is doing. Is that idea sort of making sense? It's a good time to pause. Questions on this? Perfectly, yeah.
So in PCA, are we trying to reduce the dimension?
Yeah, exactly.
So we are going from this to this.
So our data starts out in 3 dimensions. So these points live in a 3D space, right? And then these new points here, I can describe each one of them if I tell you 2 things. I have to tell you, how do I make the plane? For here, I would tell you 2 vectors that I can make the plane from. That's the B matrix. And then for each point, I give you 2 coordinates in that plane. And that's the ZI, tells me where those individual points are. So those are the things we have to design. And it turns out that the optimal 2 vectors for defining that plane, or in this case, this line, all you do is you look at the covariance matrix of your data, and basically you look for the principal eigenvector, which is sort of like in which directions is it fattest. And any direct dimensions where it's narrow, those are the ones you throw away.
So previously we used the entire data set.
Yeah, previously, like if you don't do any compression, you would have 3-dimensional features. So these are just numbers in 3D.
And we used the complete sample covariance data. But here in that equation that you showed, we are considering only the highest eigenvector or something.
Yeah, So we're basically, we're saying, how do I come up with a representation of my data set that has lower dimension? So each point now is dimension 2 instead of 3, and it lives in some hyperplane of the original, feature space. And PCA says, let's make that hyperplane so that it minimizes RSS. Yeah.
Without knowing the labels, how can we do it in an optimal way? Because you might say based on how the way they are spreading, but like in this case, the part that we are removing, what's the informative?
So there are no labels here. So our criteria of optimality is RSS. So this is the uncompressed feature. This is our approximation. We want the squared error to be minimized between them. So there's no labels. So like don't think of the red and the blue here as labels. I didn't make this figure. I think the red and the blue is just meant to show you on which side of the plane the samples are on.
So we finally don't want to do it for the labeled data, we just want to start with the labeled one, but our data should have any label in it.
Generally speaking, PCA doesn't talk about labels at all. So you don't need any labels, and you can apply it to a data set for which you have no labels. So if you also have labels, then PCA is going to ignore those labels to do its thing. And there's a problem with that in the sense that if you really want to do this compression and still have it work well for your labels, PCA may do the wrong thing. And I'll show you an example of that later. So there's other methods that try to do dimensionality reduction while preserving the label information. So LDA is an example of that. We're not going to get into the details, but I'll mention it later. I'll show you an example and give you a link. So PCA is, generally speaking, like if you're trying to do classification and you apply PCA, your classification will work certainly no better and usually a little bit worse, or maybe a lot worse. So that's not really the motivation. The motivation is, for some reason, you want to compress your data, or you want to visualize it. And visualization is just something you do for exploration. So nothing is lost if you shrink your features down to 2 dimensions so you can visualize it.
Maybe just like to visualize some of the important features, something like that.
Yeah, I'll show you pictures. I'll show you a lot of pictures of the visualizations.
Can I think of this as just generalized linear regression?
Well, so in regression, we always have the idea of we're trying to predict some targets. So here we have no targets.
Oh.
And what are we doing here? Classification?
No, we're not doing classification. We're doing dimensionality reduction.
Oh.
So maybe this is easier. So you have data in 3D, right? All those points live in 3 dimensions. And there's no labels, like there's no colors or anything. All you want to do is you want to find a line that is the best fit to your data in the sense of RSS. So you want to minimize those squared errors. Right? So there's no labels at all.
So that line is just indicating the approximate value of the value if it is on that line. Just trying to approximating the data.
Yeah, so this right here would be the approximation of this data point on the line.
Yeah.
And this would be the approximation of this one. And by putting the line exactly where it is, you minimize the sum squared approximation error.
So the approximation will be better.
This is the best possible approximation according to RSS. RSS is the criteria, so it's optimal in that sense. It may not be optimal if you want to take this and do classification with it, because RSS and classification are not necessarily well matched. And because this RSS has nothing to do with any labels. So it could be terrible. Maybe like for some reason this, I'll show you an example, but this can throw away all the information useful for classification while still minimizing RSS.
And also just to clarify, what is that in that equation in the previous slide? X is equal to BCI. What are the B and CI?
So B is going to be it's just a matrix. We think of it as a dictionary. It's a matrix whose columns we take some linear combination of to approximate xi. So if xi is a d-dimensional vector, I have a set of d-dimensional vectors inside B. I have a total of r of them, if r is like basically what I call the rank of the approximation. And now every xi has to be made with a linear combination of those r vectors. If I use d vectors, then B is a square matrix, and I can perfectly approximate all my xi's without any loss. But as soon as the matrix is no longer square, but it's tall, now I'm not including some subspace within my data, and I cannot match xi in that subspace. So I'm going to lose something. And here, generally, you use a small r, so you're going to lose maybe a lot. But maybe not. If your data like is mostly in a single subspace, then you don't lose that much with PCA. That's the whole goal, is finding the principal subspaces that your data lives in. Okay, good. Hopefully, yeah, I think it's maybe more clear now. Any more questions? Yes.
Is it necessary that if we go, for example, d equal 3 to 2, it might be better than d equal 3 to 1? Or
Generally speaking, the more you compress, like things only get worse. They can, if you're lucky, they stay the same. But generally speaking, the approximation error grows as you reduce R. Yeah.
Is B a set of vectors that span the space that pointing to the direction of the approximation?
Yes, exactly. B, the columns of B tell you exactly the vectors that span this subspace.
Are they supposed to be like unit vector or any
It doesn't matter. So the way that we set them up, they are unit vectors. But if I gave you if I scaled them, it would still create the same subspace, right? Or even if I took some matrix, if I did some linear combination of these two and got two new vectors that still were linearly independent but lived in the same plane, that would also be fine too. Yeah, so those are all solutions. But the simplest way to say it is if we build them from these eigenvectors, as we'll see, the eigenvectors are all unit norm, they're unit vectors, and they're all orthogonal to each other also.
And also, the values, not the values, the meaning of the D and the R. Does D indicate the dimension of the data and R indicate the dimension of the same data in the feature space?
Yeah, D is the raw feature dimension,
Yeah.
and then R is the dimension of our approximation. So in this case, I have R equals 2, and in this case, I have R equals 1.
Yeah.
Yeah. Okay. Excellent. I think everyone is synchronized. So, okay. So now we'll do the derivation. The derivation is a little bit involved. So we'll just go through it. But basically, the derivation has two steps. The first one is we optimize the coefficients zi, all of them, for an arbitrary fixed b. And then once we know those zi, we can plug them in and optimize b. And the first step actually is super easy. So if you want to optimize the zi's for any fixed b, you can actually optimize each individual zi, and you just have this problem here. And this is exactly the same problem we saw back in Unit 2, although there we had different variables. We had y, a, and beta, but mathematically the same derivation would apply that we use there. And when you do that derivation, you find that the optimal zi is exactly this. It's b transpose b inverse times b transpose xi. Okay, so now we know that. We take this result and we plug it back into our loss function. So our loss function, if you remember, was this one. This is our loss function. So now that we solve for zi, we plug that in here. And then the new loss function that we get looks like this. sorry, this is the loss, and this is our optimization. So here's the ZI, and we can write this in a slightly different way. We have two things multiplying xi, so I could write this as the matrix I minus this times xi, right? Because if I multiply that through xi times identity is xi, and xi times this is this over here. Okay, but this allows us to describe this thing here and give it a name, and it's a very special matrix. It's called an orthogonal projection matrix. And in particular, there's two of them, as we'll see. This one here is also an orthogonal projection matrix, and they're kind of complements, this one and this one here. This one has this little perpendicular on it. So I'll describe that in a moment. Is everybody good so far? Okay, so let's talk about orthogonal projection as an idea. I'm sure you guys have seen this before somewhere. So let's first talk about the notion of a subspace. And in particular, if I say I have a matrix B and I talk about its column space, what I mean is that I'm talking about the set of all vectors BZ such that Z is any real, any vector with R real numbers. So in other words, I'm talking about all linear combinations of the columns of B. So in this picture, this here would be the origin. And if B would be any two vectors in this plane, then by taking all the linear combinations of those vectors, I get this entire plane. Right, so this plane is the column space of the two vectors that define it. So that's what we mean here. And now, in terms of projection, the orthogonal projection of a vector x that lives somewhere in the original space onto this column space is basically just the closest vector to x within the column space. So here is x, it's a vector here. You can visualize it if you want with its root at the origin ending here. And now if you say, what's the closest vector to x in the plane? It's kind of like if you would project a light directly from above, you would see this shadow down here. This is the closest vector to x in the plane, and we're calling it x hat. And the important thing about being the closest vector is that the error between x and x hat is orthogonal to the plane, right? If I said the closest vector is here, you'd say, no, that doesn't make sense because this point is actually closer to here than this point. So another way you can think about it is if you start here and you blow up a spherical balloon, you just keep blowing it up and you ask, where is it first going to touch the plane? It's going to touch it exactly at this point that is orthogonal to the plane. So is everybody good with that? We have x, we have its projection, and we have its projection error, E. Okay, so here we have x equals x hat plus E, and x is in the column space, and E is orthogonal to the column space. And if you actually want to compute these, what you do is if you want to compute x hat, you multiply x by a certain matrix, which is this guy. This will compute x hat from x. And if you want to compute E, you multiply it by that orthogonal complement, which is just I minus this matrix. So those are the matrices that give you your x hat and your E. Okay, these are called orthogonal projection matrices, and they have essentially two and only two properties that define them. First, they are symmetric, so the matrix equals its transpose. And second, they are what's called idempotent, meaning if you think of PB, okay, so it means that if you square PB as a matrix, it gives you PB. Another intuition is if you think about multiplying by this matrix as the act of projection, It's like saying if I project x onto the plane and then project x hat onto the plane, that's no different from just doing the first step, right? Because once x hat is in the plane, if you reproject it in the plane, nothing happens. So that's why, square, cube are all the same as doing it once, PB. Okay, so those are basically the two properties of these orthogonal projection matrices. And another interesting outcome of this is if you look at the eigenvalues of these matrices, we'll talk more about eigenvalues in a moment, that you'll find that this PB has R eigenvalues that equal 1, and all its other eigenvalues are 0. And meanwhile, its complement has R eigenvalues that equal 0, and all the other ones equal 1. And this will be useful at some point later in the derivation. So this is kind of the idea behind orthogonal projection. You can think of this using this matrix operation where you have these very specific matrices here that are symmetric and idempotent. Okay, is everybody good with this? Okay. So now when you think back to PCA and remember how we derived this and we said we can give this a name, now we actually have a meaning too, that we can see what the cost is and understand it from this perspective. So this PB perp times xi is basically just the error vector for the plane defined by B and the sample defined by I. So for this, xi here, this is PB perp xi. It's this vector, of course, you have to go back to the origin, but basically it's this vector. And this says, let's minimize the sum of the squares of the norms of all those error vectors. Okay, sum squared projection error. Is everybody good with that? Okay, so now we have to get into some of the linear algebra for how we actually do this. So let's define our cost as JB, and we know from above this is what it is. And now we know also if I have a vector, I'll just call it little a, and then the norm squared, we know back from unit 1 that this is A transpose A. That's another way of writing the Euclidean norm squared. And so we're going to apply that here. We're going to write this norm squared as that vector times its transpose on the left. And the next step is to remember that this PB perp transpose, because it's symmetric, I can get rid of the transpose if we want. It's the same thing. And then also, this is like PB perp squared, and that means I can remove one of them and simplify this down to this. Okay, everybody with me so far? Okay, so now let's recall the definition of the trace. So basically, this is our goal. Our goal is to somehow express this in terms of the sample covariance matrix. The problem is, we see the ingredients of the sample covariance matrix, which is this pair of xi's, but there's a few issues. Namely, one of them is that there's this PB perp in the middle. We want to somehow get this out of the middle. So this is where we can use the trace to our advantage. So the trace of a matrix A is just the sum of the diagonal components of A. But the reason we like to use the trace is that for a matrix AC inside a trace, you are allowed to swap the order, which is something you usually cannot do with matrix multiplication. But once this is inside a trace, you can. So the trace is kind of magic that way. Now this term here, if you think about it, this is a row vector times a matrix times a column vector. This is just a scalar. And if I have a scalar here, the trace of the scalar is just the scalar itself. So that means that I can write trace of this without changing it. I'm just taking the trace of a scalar. But once this stuff is inside the trace, now I can move the xi to the left by this rule. Or I can move this one to the right, either way, which allows me to get this equation. And now, because the trace is linear, and multiplication by this matrix is linear, we can move the sum all the way through until it's inside the trace and right up against the I-dependent terms. And finally, all we have to do now is scale this by sneaking in a 1 over n and compensating with this n over here. And finally, we have our covariance, sample covariance matrix. Okay, so we've basically taken this version of the cost function, and now we've said n trace PB perp times Q. Is everybody with me so far? Okay, any questions on any steps here? Okay, so now we can start talking about eigendecompositions. So first of all, eigendecompositions of non-symmetric matrices can be pretty complicated. They can have complex valued eigenvalues and so on. But if you work with symmetric matrices, everything gets a lot easier. You're guaranteed that the eigenvalues are real and that the eigenvectors are orthogonal. And there's one more thing. If the matrix is what's called positive semi-definite, there's one other simplification. So what is this positive semi-definite? What does that mean? If you say a matrix Q is positive semi-definite, that means that when you put it inside this quadratic form with any vector x, that this is guaranteed to be non-negative. Let's prove for ourselves that this is always true of a sample covariance matrix. So if we have a sample covariance matrix, this is our Q, and now we can, by linearity, we can move the X transpose in here. We can think of these as two different things. Both of them are scalars, right? Row times column. So because they're scalars, I can always transpose a scalar, and it's the same thing. So if I transpose the second one, that actually allows me to swap X and Xi, and then you notice that we have the same thing squared. And finally, the sum or average of squared things can never be negative. So this must be greater or equal to 0. Okay, so now, in addition to being symmetric, if I have a positive semi-definite matrix, then we have this very nice eigendecomposition of this form. It means you can take Q and you can write it as a matrix V times lambda times V transpose, where V is what's called an orthogonal matrix, and lambda is a diagonal matrix of eigenvalues that are guaranteed to be non-negative. So that non-negativity comes from that property. And the symmetry is what gives you basically these other properties. And now, with regard to orthogonality, what we mean by this is that if we have a special matrix where every row and every column is unit norm, and every column is orthogonal to all the other columns, and every row is orthogonal to all the other rows. And one way to see all those properties together is if you take V and multiply it on the right by V transpose. Actually, let's do this one. So imagine you have the columns of V. Now the same columns get transposed here. That means that when you take inner products of those columns, the identity matrix means, look, along the diagonal, that's when you take, let's say, the first times the first. The fact that you have an identity means that has norm 1. Now if you take the second times the first, you're at an off-diagonal element here, which means that gives you an inner product of 0, meaning they're orthogonal. So this is how you can see the columns are orthogonal, and this is how you can see that the rows are orthogonal. So that's what's special about these V matrices. Orthogonal matrices and the diagonal ones are non-negative. Everybody good on these? Have you seen this before somewhere? Okay, great. And we're going to assume one other thing, which is that the lambda i's are sorted from large to small. Basically, when you use a solver like in Python or MATLAB, an eigenvalue solver, you're definitely not guaranteed to get them sorted, but you can always sort them manually if that's useful to you. You can always do it. So we'll just assume that that's been done. So here's this main theorem that we will prove in a moment, but the theorem says that to minimize this cost function, which is the one we derived on the previous page, we choose B to be the capital R principal eigenvectors of V. So that means that if we've done this sorting, we're just going to take the first R, capital R columns of that V matrix. And that's going to be the optimal B. And like I mentioned before, actually other things work. You can take this matrix, tall matrix, and you can multiply it on the right by any R by R square matrix as long as it's invertible. And that will work too because it gives you the same column space. But this is just the one that's easiest to talk about. Okay, so this is basically the idea that if this is true, then basically we've proved PCA as I described it way back here. Like we've proved this. Okay. All right. So any questions on the eigen stuff? Okay. So let's see how this plays out. So this is where we are with our cost function. We want to minimize this. And we can plug in for PB perp, I minus PB. And because the trace is linear, we can expand that into n times the trace of I times Q, which is just this, minus n times the trace of PBQ, which is this. And now, since we're optimizing B, we don't really care about this first term. In fact, if we're minimizing this, that means we want to maximize this trace PBQ. So let's work on that. And we're going to call that thing a utility. It's like the opposite of a cost. So we want to maximize this utility, which is just the trace PBQ. So how do we do this? So first step, let's plug in our eigenvalue decomposition of Q. Next, let's use our trace property to move this to the front. And finally, if you look at this, there's an interesting structure here. So there's this matrix here that in general is a dense matrix. It has non-zero coefficients everywhere. But what we're actually doing is we're multiplying it by a diagonal matrix. And then we're taking the trace. So if you think about what's going to happen here, this diagonal term is going to multiply this entire column. The next one will multiply this column, and so on. But at the end of the day, we take the trace, which only looks at the diagonal, sums the diagonal terms of this. So that means the only elements of the left matrix that are involved in the trace are actually the diagonal ones. Yes, there's other off-diagonal ones too, but those don't make it through the trace. And in particular, what happens to the trace? So these guys here are what I call alpha j over here. And then these other ones are the lambda j's. So basically, the trace is just going to be the sum of whatever the diagonals of this are, element-wise multiplied times these diagonal lambda j's. So in terms of optimizing B, we can kind of, for now, just reduce the problem to figure out what are the optimal alpha j's, and then we'll figure out the B that gives us those alpha j's. Okay, so here's the full definition of the alpha j's. We create this full matrix, and then the jth one, we just look at the jth diagonal term of this matrix. And if you want to even go further, okay, how do you compute the term, that jth diagonal term? Well, you would take the jth column of V here and here, and then that would give you, you'd make the quadratic form like that, and that would give you the alpha j term. Okay, so these A's actually have two important properties that we're going to exploit. So let's look at alpha j again. We have this definition where PB is this orthogonal projection matrix, and we know because it's idempotent and it's symmetric, we can write PB instead as PB transpose times PB. We actually did the opposite thing before. Now we're kind of going backwards and we're expanding it this way. The reason we're doing this is so that we can again go backwards and write this thing as the norm of this squared. Now, because PB has eigenvalues either 0 or 1, it can never grow basically the length of Vj. It can only shrink it, so we can upper bound it by the squared norm of Vj, and Vj was a unit vector, so that's 1. So in other words, you can see that this can't be negative. So it's somewhere, this alpha j is somewhere between 0 and 1. Okay, so any questions on that? Okay, so the alpha j's are somewhere between 0 and 1. Now there's another important property. If you sum up all the alpha j's, let's see what happens with that. So to sum up the alpha j's, basically we're just, summing this, that is the trace of that matrix. And now we can play our trace tricks again. We can move V to the front. And now, because V is orthogonal, V transpose V is identity. Multiplying identity times a matrix does nothing, so we just have trace PB. Now we can plug in our original expression for PB, which is this. Using the trace again, we move B transpose to the front. And now we have a matrix times its inverse. And that will give us the identity matrix of dimension R. And if you take the trace of an identity matrix with dimension R, you're guaranteed to get R. So at the end of the day, it means that when you sum up all these alpha j's, you know you're going to get R. And individually, the alpha j's are between 0 and 1. So now we can state a very simplified optimization problem. We want to find this set of alpha j's so that all the alpha j's are between 0 and 1, that they sum up to R, and that they maximize this quantity here. And I'm going to argue that this is a problem that you've all solved before in real life, many problems like it. And I'll phrase it this way. Imagine that you go into a store and you're going to buy some food. And this store has D different kinds of food. And they have 1 pound each of every kind of food. And you are going to buy a total of R pounds of food, and you need to figure out how many pounds of each food to buy. So you can buy somewhere between 0, which is none, and 1, because that's all they have, and you're going to buy a total R pounds of food. Now to figure out which foods you're going to buy and how much, we're going to think about these lambda j's, which is how much you enjoy the jth type of food. So if you don't enjoy it at all, it's 0, but if you love it, it's large. Okay? So this is, you could kind of say, is like how much total enjoyment are you going to get? Because you're going to buy this many pounds of that kind of food. So how do you spend your money in this case? What do you think? You go in there, you have to buy R pounds, you have all these foods, some you like, some you don't like. Max 1 pound per food. What are you going to buy? Yeah, so alphas are upper bounded by 1.
So set 1 goes to 1 and then it's to 0.
Exactly. Yeah. You're gonna buy the max that you can of the foods that they have. So that you're gonna take your R favorite foods, you're gonna clean them out in those foods, and then the rest of the foods you're not gonna touch, so you can keep that stuff. Right? That's the solution to this problem. So so here, I already did it in words, but basically this is what I just described. And this is our solution. We're going to choose alpha as 1. Because we already ordered our lambda j's from big to small, we're just going to choose alpha j as 1 for the first capital R j's, and then 0 for the remainders. And now the question is, how do you make a B to give you those alpha j's? Because remember that the alpha j's were kind of defined by this B. We can just set B to the first R, the R principal eigenvectors. And to see why that's the case, we can write the PB matrix. If we did that, then the PB matrix looks like this. And remember that because this is an orthogonal matrix, this V transpose V is identity, so we can simplify it like this. And now finally, to make our alpha j's, we're going to take this matrix and put it in a quadratic form with these little vj's. And if this j is between 1 and capital R, then when we put it in that quadratic form, we're going to get 1. But if this j is not in this set of columns, it's orthogonal, so our alpha j will be 0. Okay, so this is finally, we've proven this Eckert-Young theorem. We've basically proven well, almost. The very last thing to do is to figure out the zi vectors. But basically, now that we know what B is, the zi vectors, we said, are this. So basically, because our B has orthogonal columns, this all goes away, and this is just going to be V R Xi. So basically, we've proven the PCA idea. So here's a summary. So we have our centered data Xi, meaning we removed a mean. PCA approximates Xi by this product of this V matrix, which contains the R principal components of the sample covariance matrix Q, and has this R-dimensional vector Z hat, which we make like this. And that's how we get this nice approximation in a lower dimension. Okay. So any questions on any part of the proof or anything high level here? Okay. One more slide then for today is how do we quantify the performance of this approach? That will help us choose the rank R. We've done this before with linear regression. When we talked about linear regression, we wanted to quantify how good of a fit do we have. We used R squared. Don't confuse this R with this R. This is not italicized. So if you think back to then, the definition of R squared is 1 minus RSS over n times the target variance. Well, we don't have targets now. So what's the closest thing to target variance? Is the sum of all the feature variances. That would be the trace of the sample covariance matrix Q. So basically, this thing called proportion of variance, it's the same intuition as R squared, except it works for PCA because it's done not with targets, but with features. And we want basically proportion of variance to be as close to 1 as possible because as you can see, with a perfect fit, you would get 0 RSS. That's the highest you can get, 1. So that's our goal, is to get 1. And it turns out that the worst you can do is 0. So let's see the details now. Okay, what is this n trace Q? Well, we already saw for Q, we have this eigenvalue decomposition, and we can move this over to this side, at which point it cancels the other V, and then you can see that n trace Q is just this quantity. For RSS, we also saw that this is the loss we derived earlier, and we can split this into 2 terms. The first term is exactly this, and the second term is similar to the first one, except rather than summing over all D eigenvalues, we sum only over the R that we're modeling. And when you subtract the 2, you essentially get the little lambda i's that you did not model. These are all the ones you didn't model. So the ratio, this POV thing, if you plug everything in, you finally get this quantity. So here is a total energy that you modeled. You're looking at the sum of the lambdas up to R, and here's the total energy. And so you can see as R approaches D, this approaches 1. But if you have a very small R and you have lots of energy that was not captured by your model, then this could be a number much closer to 0. Okay. So this is basically what we use to choose R. So if you, for example, if you made a plot of POV versus R, let's see, do I have a plot? Here's a plot of POV versus R number of principal components. You can see it shoots up, and then at some point it gets really close to 1. And you might say, okay, that's good enough. I can do my, stop my approximation here. I don't need to use 1,300 principal components. Okay, so we'll leave the fun stuff for next week. We'll show some nice applications of this to modeling face data. But any last questions on PCA? Okay, great. Have a great weekend. See you guys next week.